This is the last section of the second lecture, and here what we want to do is we want to talk about different solar technologies. The first thing we want to address here is, remember when we have the single band gap material, we get efficiencies of, let's say, 24% or so for a silicon. Now what we want to do is we want to increase the efficiency of the solar cell. What is that we can do? And the second thing is we use quite a bit of material on a single silicon wafer, and we can go down reducing that material, and then we get what's called a thin film PV cells, and they're supposed to be low cost, and we'll talk a little bit about that. And then we also talk about organic solar cells, and we briefly mention them, and their references are given underneath each of these slides, so you can go and learn more about that. So the first thing we want to look at is multi-band gap devices. So these are means that there are several materials, and a schematic is simply shown the energy levels here in this particular case, the gap energy. So the light is coming here. These are shown in the visible light colors here in this case, the blue and the green and the red. So the way it is there is a first gap material where the blue frequency is utilized to extract the energy from that, and then it filters through. Rest of it is the next band gap, which is associated with using the frequency for the green color, and then the remaining red color will pass through, and then you have a different gap material. So by using the different gap materials, so essentially we are going to get some power out of this, and some power out of that, and some power out of this one. So when we add these powers together, and of course the incident power remains the same, the efficiency of the cell is going to go up. And in fact, in the laboratory conditions, the efficiencies of almost up to 63% has been realized for multi-gap devices. So remember, if you have one gap device like 1.1 electron volts for a silicon, the observed efficiency, cell efficiency are about 24-25%. So these kind of multi-gap, although they're quite expensive to manufacture, but these are used mostly in the satellites in the outer atmosphere, where the incoming radiation has quite a large value of 1367 watts per meter square. Then you have 63%, that means almost about 2/3 of that you can get. So that means about 1000 watts per meter square you can obtain electricity from these multi-gap devices. And so the area required to power the satellite will be less, so hence they use them in the satellites currently in space. So this is what is called a 3-junction solar cell, which we have just looked at. Instead, now we have a 4-junction solar cell. Again, it's represented by different colors with the different band gaps. So you can see that these are given by the band gap. Each of the color represents that. So in the light blue color is this one here, which 1.8 electron volt band gap, and this one is 1.4, and the yellow is about near silicon 1.1, and the other one is 0.7. So if then you can see that the entire spectrum, the energy in the entire spectrum is utilized, and then you get quite high efficiency, and theoretical efficiency for this is greater than about 52%. And this is the spectrum. And so here again I am showing you the band gap 2.0, which is in this range here. And you remember that we talked about the energy in this part of the curve was not utilized before. This is wasted. So now in this particular case that can be utilized because the band gap is high. So the high energy electrons can be captured in this particular case. Then you come to about 1.5, that is the one which we have used before. You remember entire to the left of this curve we were unable to capture the energy. Now of course we will do that by using these 1.0 and 0.7 electron volts. In this fashion, now you can essentially capture from energy from here all the way to about somewhere around here. So earlier we were only capturing energy in this region here. Now instead we extend the region to almost up to here. So you can see that you can get much higher energy extracted from that. And these are some of the efficiencies of the different band gap materials. So 1.1, what we were looking at is if you lose the A1.5 spectrum, this is the dashed line, and the solid line here, which is the AM10 spectrum. So this is the AM10 spectrum in this particular case, and this is the AM1.5 spectrum. And you look at here, gallium arsenide in this particular case, CDTE and CIGS and so on and so forth, and you can see they have all around less than about 30%. So essentially what you do is, if you have silicon, for example, here 1.5 spectrum, you get about 24%. Then you have different another gap material, you will get about 20% or so. You keep adding like that. At 0.7 in this particular efficiency is less than about 20%. So you have different band gap materials at different efficiencies, and when you put all of them together, you in this particular case you get 52% efficient cell. So that isn't too bad. You remember that the silicon alone you seldom get more than about 25% or 26%. So this is one way to develop a solar cell using what's called 4 junction solar cell, or in the previous one it's called multi-band gap devices. So this is the best way to increase the cell efficiency. Now second thing what we want to do is we want to make them cheaper, because not only you want to improve the efficiency, the cost has to come down. One way to do that is we use the less material deposited onto the supporting substrate. For example, in silicon we use quite a bit of silicon, and that is quite expensive. It almost costs about, right now its price has come down quite a bit thanks to Chinese manufacturing. So now it's about $25 a kilogram of pure silicon. So you go through, take the silicon, metallurgical silicon, and it roughly takes about 250 kilowatts hours of energy to convert the sand from metallurgical sand to all the way to the pure silicon. So if the cost of electricity is, for example, 10 cents, is almost cost you $25. But the process has been improved quite a bit, and the Chinese and the electricity, most of them is subsidized. As a result, the cost of today's silicon is about $25 a kilogram. So one way to reduce the cost is to make them thinner. And the additional advantage to make them thinner is you get the flexible substrate. So like this, for example, you can see you can bend them, and you can use them in a variety of applications. For example, there was a company in Switzerland where they put them on the ski jackets and things like that, where they can, while you are skiing, you can power your iPads, iPods and iPhones and etc. But the only difficulty with that is in the second generation shells the efficiencies have been low, but however now with CIGS, which is this materials which they use, the efficiency reached almost about 20%. And MR for silicon, the efficiencies are reached about 10%, and cadmium telluride is about 15% or so. So for example, this CIGS is almost about 20% efficient right now, and these are about 15%. So that is almost these are cell efficiencies, not the module efficiencies. Module efficiencies, CIGS may be about 14% or so, which are quite similar to the low cost silicon modules. But the only problem is these are difficult to manufacture, and as a result the scaling up of the manufacturing facilities is quite tedious, but people are beginning to make advances in this. So eventually what we want to do is we want to go to either CIGS and CDTE, the First Solar, which is a major manufacturer of CDTE. One of the problem in these cells is they have cadmium in them, and what happens when the cells after their service is over, which is about roughly 30 years 20 to 30 years, when you try to dispose them off, the cadmium will pose a problem. So there is a difficulty in using the cadmium telluride in terms of the disposing of the modules when their lifetime is over. So the most of the companies now are trying to develop the CIGS cells at a low cost, at the same time with efficiencies similar to what the silicon solar cells are. And these are the CIGS modules, and in fact you can see that module efficiency in here is about 15.5%. This is about 2012. I think they are improved it to almost 20%, right? 19%, I think, module efficiency. And the prediction is it's in fact less than this. So, but you can make it around 50 cents a watt. However, the silicon, crystalline silicon, first generation cells have come down in price, and these guys are having difficulty competing with those cells. However, they have some advantages. For example, one of the advantages of these flexible solar cells is that you can put them, for example, on the swimming pools, so that you don't have to use the space on your roof, and they float on the swimming pool, and then they're light enough so you can absorb the solar light and produce electricity. Or in the ponds, where it serves two purposes. Not only they are producing electricity, they also stop the evaporation of the water from the ponds. So there is a strong interest in these modules now to put them in irrigation canals, covering the irrigation canals, and retention ponds in the coal power plants and things like that. So these CIGS modules can have a tremendous impact in special applications like that. Now there is another type of technology. These are called the photoelectric solar cells, and these are of course this is a transparent material, and these are the kind of cells. You have electrolyte in here, and they have the titanium dioxide or some kind of a particles in this case, and when the light is shine on this electrolyte here, and the electrons which are sitting in this will jump and to the higher level and produce the current. And these things have very low efficiency, and typically the efficiency is about 5%. But the advantage of this is, for example, when you have the windows where you have two glasses in between, typically what you do is you put argon or nitrogen in these things. Instead, they become still transparent enough that you could fill those between the two window glass. You can fill this liquid and use these particles in there, and you can keep generating electricity. So although they are low efficiency, but since you have to have windows, it may not be that expensive to use windows with photoelectric chemical cell as opposed to some argon or nitrogen in here. And this is another one called organic polymer solar cell, and these again have the difficulty of having very low frequency, and but they can be extremely low cost. This is right now is the technology comes from in Switzerland, in the University of Lausanne, and that's where this originally made improvements in this organic cell technology. But I think in the modules now you can get it about 5%. Again, these things can be transparent. You can use to replace the regular windows, and there are some windows I think placed in New York City in the Times Square in one of the buildings with these cells, where they generate the power. At the same time, they're also transparent, so you can look out and do things like that. So these are of course the few technologies people are working, and you can go to the websites of these laboratories to learn more about these advanced technologies. But however, the silicon solar cells cost has become so low now, people are not paying attention to these advanced technologies further. Thank you.